Hello friends, welcome to mewlessons.com. So today our topic is about DC circuits. In this chapter we will learn the basic concepts about current, voltage, resistors. We have two laws, Ohm's law, Kirchhoff's law, and there are two types of circuits we will read about. Those are series circuits and parallel circuits, and we will deal with some simple DC circuits. So first of all we will start with DC circuits. These DC circuits consist of maze of loops, nodes, branches in an undirected graph, and several components like resistors, diodes, capacitors, etc. So depending on those, we deal with the behavior of the components. Now the first is voltage. What is voltage? Voltage is the difference in the electric potential between any two points. If there will be no difference between the potentials, we won't find any voltage. The concept of ground is also useful in this stage. The SI unit is volt. Now the next part is about current. You are familiar with what is current, the general definitions. It is the movement of charge. It is the time derivative of charge passing through a circuit branch. Its unit is given in ampere. These are all simple things you must know before reading DC circuits. Now look at this picture. This picture shows the resistors in series and parallel connections. In series connections, resistors R1, R2, R3 are just added up to give the equivalent resistance, but in case of parallel, it is just the reciprocal to get the equivalent resistance. Now the next part is the first law, that is the Ohm's law. Current in the resistive circuit is directly proportional to its applied voltage and inversely proportional to its resistance. As you can see in this picture, a battery is connected to a component, a voltmeter is connected in parallel, and an ammeter is connected in series. So the resistance will be V divided by I. Here the current is directly proportional to voltage and inversely proportional to the resistance. Now the next part, that is the Kirchhoff's law. There are two Kirchhoff's law, those are KVL and KCL. We are most familiar with these two laws in dealing with DC circuits. The first law, Kirchhoff's voltage law. In this case, the sum of the voltages taken around any loop is 0. That means the start and the end points are identical, so there is no potential difference, and hence in that case the sum of the voltage is 0. The next is Kirchhoff's current law, well known as KCL. The sum of the currents in entering the node is 0. The consequence is the conservation of charge. The total amount of charge entering into the circuit is equal to the total amount of charge existing. Now look at this picture. These two diagrams shows the respective parallel connection and series connection. The first case, VV is the EMF and R1 and R2 are two resistances connected in parallel, 6 ohm and 2 ohm. In this case, the voltage across the two resistors R1 and R2 is same, and as a result the currents are different. But in the second case, the same VV is the EMF produced and the two resistors R1 and R2 are connected in series. So there are several voltage drops in the R1 and R2. In this case, currents are same. So my motive to show you this picture is to deal with the parallel series circuits. Now suppose if you come across this type of circuits, internal resistance R1 along with EMF, internal resistance R2 along with EMF E2, and the second picture is a bridge connection of R1, R2, R3, R4 and RTH with the external resistors and an EMF. So what should you do in this case? Neither these two shows the parallel circuit connection nor the series circuit connection. So in this type of complex cases we use the Kirchhoff's law. Either we can use the KVL or in case of KCL the loop current is 0, and in case of KVL the loop voltage is 0, showing the conservation of energy and conservation of charge respectively. So the next topic is about series resistors. In this case you can see the series configuration of the resistors. It is just a summation of resistors 1, 2, 3, 4 up to n. More the number of resistors, more is the resistance. When the series registers all have the same value, we can write the net resistance as N into R, where N is the number of resistors in the string. In this case, Is equals to E by RT. RT is the total resistance. Once RT is known, the current drawn from the source can be easily known, and this RT depends upon the configuration of R1 and R2, in which configuration they are set, that is either series or parallel. In case of series circuits, the polarity of the voltage across the resistors is determined by the direction of current. V equals to R1, V2 equals to IR2, and so on. Now, the next is voltage source in series. Voltage source can be connected in series. The voltage source can be dependent source or independent source. But for the time being, we will deal only with the independent sources. Voltage sources can be connected to increase or decrease the total voltage applied to the system. Net voltage is determined by summing the sources having the same polarity and subtracting the total sources having the opposite polarity. Now this is the Kirchhoff's voltage law. You can see in this picture the law has been applied. KVL, the ring goes in clockwise direction. The current entering into the EMF is taken as positive and current exiting is negative. This Kirchhoff's law has various things. The applied voltage of a series circuit equals the sum of the voltage drops across the series elements. The sum of the rises around the closed loop must equal the sum of the drops. Do not treat a voltage drop across a resistive element differently from a voltage drop across a source. These two are very different things. Now this is a very important thing, voltage division in case of series circuit. In this case, we use the voltage divided rule. It is very important in dealing with series circuits. Vx equals to Rx into E by RT. The voltage across the resistors in a series circuit is equal to the value of the resistance times the total impressed voltage across the series elements divided by the total resistance of the series element. This rule can be extended to voltage across the two or more series elements if the resistance includes two resistance of a series, then the voltage to found across. We will deal with some of the questions, so you do not need to worry at this moment. This is a format of interchanging series elements. Elements of a series circuit can be interchanged without affecting the total resistance, as you can see in this picture. EMF 75 volt is applied across R1 and R2, 10 ohm, 5 ohm, R3 as 20 ohm. As these three are connected in series, so we can just interchange the values. It won't change the circuit, everything will be same, just the drop across will differ. This is the general notations of voltage sources and grounds. Now the next topic is about the parallel resistors. In case of parallel resistors, the voltage across them is constant or same. For resistors in parallel, the total resistance is determined as 1 by RT, that is the total resistance, equals to 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by R to the power n, where n is the number of resistors used. Once the right side of the equation has been determined, it is necessary to divide the result into 1 to determine the total resistance. If we note 1 by R1 as G1, Gt can be represented as G1 plus G2 up to Gn. This is the opposite effect of increasing the number of resistors in a series circuit. As the number of resistors in parallel increases, the input current level will increase for the same applied voltage. RT equals to 1 by R1, 1 by R2 up to 1 by Rn, as seen before. The total resistance of a parallel circuit resistance is always less than the value of the smallest resistor. This is very important to note, and this is often asked in competitive examinations. For equal resistors, RT is given as R by N and is the number of resistors connected in parallel. In case there are special cases also. The total resistance of two resistors is the product of the two divided by the sum. RT equals to R1 into R2 by R1 plus R2. The simple thing is RT equals to 1 by RT equals to 1 by R1 plus 1 by R2, and if you simplify it, we will get RT equals to R1 R2 by R1 plus R2. Parallel resistors can be interchanged without changing the total resistance or the input current. The total resistance will always decrease as additional parallel elements are added. If the voltage is same across the parallel elements, then V1 V2 will be equals to E, that is the same constant voltage throughout the circuit. But the most important thing is the current changes. Is equals to I1 plus I2, that means the net current changes in case of parallel circuits. For parallel circuits, the greatest current will exist in the branch with the lowest resistance. Is equals to I1 plus I2, that is I1 can be denoted as E by R1 plus I2 can be denoted as E by R2, and this gives the total current. The power in the parallel circuit is P equals to P1 P2 P3, and this is same and similar or identical, we can say that, like that of the series resistive circuits. The power is just the summation of all the powers across the resistors. Now when we use KCL, this is the main point in case of parallel circuits when you use the Kirchhoff's current law. It states that the algebraic sum of the currents entering and leaving the area or the junction is 0. The sum of the current entering an area or leaving it is always constant. The most common application of this law will be at the junction point when the circuits are connected in parallel. If the current arrow points away from the junction, the current is leaving the junction. If the current arrow points towards the junction, the current is entering the junction. Current as in case of series, we have read voltage divider rule. So in this case we will read about current divider rule. It is just similar, but there are certain changes. For parallel elements of equal value, the current will divide equally. This is more important, the current will divide equally. For parallel elements with different values, the smaller the resistance, the greater the input current. The current will split into ratio equal to the inverse of the resistor values for parallel elements of different values. This picture shows the current divider rule. Ix equals to RT by Rx into IT. So this picture gives a quite brief idea about the current division rule. We will use it in solving some problems. Now, voltage sources in parallel. Voltage sources are placed in parallel only if they have the same voltage rating. Unless they have the same voltage rating, we cannot keep them in parallel. So the formula derived for the current is net change in voltage, that is E1 minus E2 by net resistance, RINT plus RL2. Voltage sources in parallel can be based on batteries. Two batteries of different terminal voltages placed in parallel. When two batteries of different terminal voltages placed in parallel, the larger battery tries to drop rapidly to the lower supply. The result is the larger battery quickly discharges to the lower voltage battery, causing the damage to both the batteries. Now this is a simple thing about open and short circuits. In case of open circuit, the two terminals are kept open and we can find the voltage across the two terminals. That is, there is certain voltage difference across those 2 points given as A and B. In case of open circuit, as the circuit is incomplete, the net current is 0 even if we are giving an EMF supply. This picture gives the difference between open circuit and short circuit. Short circuit can carry a current of a level determined by the external circuit by the potential difference. In case of short circuit, there is 0 voltage across the terminals. In this case, as you can see, EMF 10 volt is applied through a fuse of 10 ampere and resistors of 2 ohm is attached. So if we use a voltmeter to measure the voltage across the 2 ohm, we will get some result. But if we want to make it short circuit, we just simply put a wire from terminal A to B, and in this case current follows the shortest path, and this symmetry is called the short circuit condition. In this case, the resistance 2 ohm has no importance and the current across the resistor is 0. So we know that V short circuit is 0 volt. So let us simplify this circuit. This is the given circuit. 6 ohm and 3 ohm are connected in parallel. EMF is 18 volt. Interresistance is 0, and resistance 4 ohm is connected with 6 and 3. So in this case, first try to realize the circuit. That is, we have got one series part and we have got one parallel part. First of all, we convert the parallel part into the series part. So we solve the parallel part. 6 ohm and 3 ohm. So resistance becomes 1 by 6 plus 1 by 3. We get it as 2 ohm. Now this part is little easy. 18 volt supply given across a series of 4 ohm and 2 ohm. Now further we solve the series circuit. We get 18 volt supply and the further resistance is 6 ohm. After that we have one EMF and one resistance, so easily we can get the current across the circuit. So the current is given as 18 by 6, that is 3 ohm, 3 ampere. Now if we realize the circuit in this way, 18 volt given across the series resistance, so we have know that in case of series we use KCL, and also we use the current dividend rule. In this case we use the voltage dividend rule. So there are two different voltages, two different resistances, and hence there will be two different voltages. If we calculate the voltage across 4 ohm, it comes to 12 volt and respectively 6 volt across the 2 ohm resistance. Now similarly, we expand it to the original size. We get that the 4 ohm resistance has 12 volt supply and the current is 3 ampere, and this 3 ampere current has to flow through the next part, which are connected in parallel. But as they are connected in parallel, the voltage should be same, that is 6 volt, and the current divides, that is 1 ampere and 2 ampere. So in this way we can realize the circuits easily and solve them. If we get the current, resistance and EMF value of the circuit, then easily we can find the other factors like power or energy or